Welcome to Systemic Stack. My name is Kabir Anand. This is episode 24 of the System Engineering series, and today we will explore distributed locking in a way that helps you prepare for system engineering interviews on this topic. When distributed processes compete for the same resource, it's easy for things to break without a central source of truth. So we'll dive into two main lock types, exclusive and shared, and see how tools like Redis and Zookeeper handle them. Showing you can navigate these implementation trade-offs is exactly what interviewers want to see when you're designing reliable, high-scale systems. We begin with the competition problem, where we'll see what happens when distributed processes clash over the same resource and how mutual exclusion provides that necessary source of truth. It starts by breaking down the two main lock types, exclusive and shared, before we dive into real-world implementations like Redis and the red lock algorithm. Now, it is not only about setting a flag, it's about reliability, right? So we'll explore how leases and time to live values keep things moving if a process crashes, and we'll address the risks of deadlocks and clock drift. We are also going to spend some time on consistency, especially why things like fencing tokens and monotonic ordering are absolute requirements to prevent delayed processes from corrupting your data. Finally, we look at the high-level trade-offs for your interviews, comparing these locks to standard database transactions. By the end, you'll have a clear framework for deciding when and how to coordinate distributed resources without sacrificing system correctness. Let's set the scene with a real engineering challenge. Imagine you're building a massive payment processing system that handles thousands of transactions a second across a global cluster of microservices. You have a specific requirement. No user should ever be double charged for a single purchase. However, because of network retries and load balancing, multiple instances of your billing service might receive the exact same payment request at the same time. This is where distributed locking becomes critical. Without it, those instances would all try to process the payment simultaneously, leading to duplicate entries and unhappy customers. The failure mode here is a direct hit to your company's reputation and bottom line. You're operating under strict constraints of high availability and low latency, yet you cannot compromise on correctness. In this production context, a local mutex on one server won't help you because the requests are hitting different machines. You need a way for these machines to talk to each other and agree on who has the right to process that specific transaction ID before anyone touches the database. Mastering resource coordination is really about mastering the chaos of high-scale systems. Distributed locking works by allowing one node to claim a temporary exclusive right to a resource across the entire network. What matters here is that in a world where nodes can fail or lag at any moment, we need a reliable way to ensure that tasks that should only happen once actually only happen once. Think about a bad job that generates a daily report. If 5 nodes started, you're wasting money and potentially corrupting the file. The primary failure mode to keep in mind for your interviews is the loss of liveness. If a node grabs the lock and then crashes without releasing it, the resource could be stuck forever. We solve this by introducing timeouts, but that leads to its own set of problems, like a lock expiring while the node is still working. Understanding how to navigate this tension between safety and liveness is the hallmark of a senior system engineer. We are going to break down how to handle these edge cases throughout this lesson. Imagine you've got 3 different worker nodes, all trying to update the same user profile or subtract from the same inventory count at the exact same millisecond. This is the competition problem. Without a locking mechanism, you're looking at classic race conditions, where the final state of your data depends entirely on the random timing of network packets. It's a huge issue because it leads to silent data corruption that's incredibly hard to debug after the fact. You might see a balance of $10 become 20 instead of 15 because two processes read the polled value simultaneously. The failure mode here isn't just a crash, it's an inconsistent database that looks fine on the surface but is fundamentally wrong. In an interview, you'll want to highlight that this isn't just about speed, it's about correctness. We need a way to ensure that these competing processes queue up and wait their turn, transforming a chaotic free-for-all into a predictable, serial stream of updates that preserves the integrity of our shared state. The core of distributed locking is about establishing a single central source of truth for resource ownership. In a distributed environment, you've got dozens or hundreds of nodes, but they all need to agree on which one owns a specific resource right now. This coordination works by having a central lock manager, like Redis or Zookeeper, that acts as the ultimate arbiter. What matters here is that it prevents the split brain scenario, where two different nodes both think they are the leader or the sole worker for a task. If you don't have this central coordination, your system effectively has no memory of who is doing what, leading to total chaos in your data layer. The failure mode to watch for here is the bottleneck. If every single operation requires a round trip to the lock manager, that central hub becomes a massive point of contention. In an interview, you'll want to discuss how to minimize this by only locking the specific granular resources you need rather than putting a giant lock over your entire database. It's all about balancing that central control with the performance needs of a distributed system. At its heart, distributed locking is about enforcing mutual exclusion. This simply means that if process A is working on a resource, process B is strictly forbidden from touching it until process A is finished. It's the digital equivalent of a one person at a time bathroom lock. What matters here is that it's the only way to guarantee that complex multi-step operations remain atomic and consistent. Without mutual exclusion, you risk a collision where two processes try to write to the same file simultaneously, resulting in a corrupted mess that neither can use. The failure mode here usually stems from network delays. If a process takes too long and the lock manager thinks it's gone, it might grant the lock to someone else while the first process is still mid-write. This is why mutual exclusion in a distributed system is much harder than on a single machine. You can't just stop the world. You have to account for the fact that exclusive is a relative term when clocks drift and networks lag. When an interviewer asks about safety, they're asking how you maintain this exclusion despite those environmental failures. Let's talk about exclusive locks, also known as write locks. These are the most restrictive type of lock you can use. How they work is simple. If a node holds an exclusive lock, no other process can read or write to that resource. Period. This is absolutely essential for operations that change data, like updating an account balance or modifying a configuration file. If you allowed someone else to read the data while it was being updated, they'd get a dirty or partial view that could lead to further errors downstream. The trade-off here is high consistency at the cost of high contention. The failure mode is quite clear. If an exclusive lock is held for too long, it creates a massive traffic jam. Every other service that needs that resource is effectively frozen, which can lead to cascading timeouts across your entire system. In an interview, you should mention that while exclusive locks are the safest bet for data integrity, they are the most dangerous for system availability. You have to keep the lock held time as short as humanly possible to avoid killing your throughput. Shared locks, often called read locks, offer a more flexible approach for high-traffic systems. How they work is by allowing multiple nodes to hold the lock at the same time, provided they are all just reading the data. However, as soon as a writer wants to change something, it has to wait until every single reader has released their shared lock. What matters here is that it significantly boosts performance for read-heavy workloads, while still preventing a writer from changing the data out from under someone's feet. It's a great way to scale, but there is a specific failure mode you need to know for interviews: writer starvation. If you have a constant stream of new readers coming in, the writer might never get a chance to acquire the exclusive lock it needs, causing it to wait indefinitely. You've got to implement a queuing strategy that prioritizes writing writers to keep the system healthy. Understanding this balance between maximizing read throughput and ensuring writers don't get blocked forever is exactly what an interviewer is looking for when discussing complex locking architectures. When we talk about high-performance locking, Redis is usually the first name that comes up. The basic implementation uses the setnx command, which basically says set this key only if it doesn't already exist. It's fast and memory first, which is why it's so popular. However, a single Redis instance is a single point of failure. To solve this, we use the red lock algorithm, which involves getting a majority vote from 5 independent Redis masters. You need 3 out of 5 to agree before the lock is considered valid. What matters here is that it provides a layer of fault tolerance that a single instance just can't match. But here's the catch, and this is a big one for interviews. Redlock has some known failure modes related to system clocks and GC pauses. If one node's clock jumps forward, it might expire a lock prematurely, letting another process grab it while the first one still thinks it's in control. You've got to understand these nuances to justify using Redis over a more strictly consistent tool like Zookeeper or etc. It's a classic speed versus safety trade-off. Lease-based locks are the industry standard for preventing orphan locks in distributed systems. Instead of a lock that stays active until the process says it's done, you grant the lock with a time to live, or TTL. One simple way to picture this is a rental agreement that automatically ends unless you renew it. What matters here is that if a worker node crashes or loses network connectivity, the lock will eventually expire on its own, allowing other nodes to take over the work. Without leases, a single crash could lock up a resource forever. However, the failure mode here is the split brain effect caused by long process pauses, like a stop-the-world garbage collection. If a process is paused for 10 seconds, but its lease is only 5 seconds, the lock will expire while the process is asleep. When the process wakes up, it still thinks it has the lock and might try to write to the database, causing corruption. In an interview, explain that you need to keep leases long enough to cover the work, but short enough to recover quickly from failures, and always use renewal heartbeats for long-running tasks. Deadlocks are the nightmare of any distributed system. This happens when two or more processes are stuck in a circular wait. Process A holds lock 1 and waits for lock 2, while process B holds lock 2 and waits for lock 1. Neither can move and they'll wait forever if you let them. To prevent this, we typically use two main strategies: lock ordering and timeouts. Lock ordering means we always acquire locks in a specific alphabetical or numerical sequence, which breaks the circularity. Timeouts ensure that if a process can't get a lock within a certain window, it gives up and releases everything it's holding to try again later. What matters here is that a deadlocked system is effectively a dead system. The failure mode often occurs during unexpected spikes in load, where timing becomes unpredictable, causing processes to back up and time out simultaneously. In an interview, you should emphasize that you never request multiple locks without a strict order and a fail-fast timeout policy. It's about building a system that is self-healing rather than one that requires manual intervention to clear stud processes. A common mistake is thinking that a distributed lock alone is enough to guarantee consistency. It's not. A lock is just a piece of metadata. It doesn't actually stop a rogue or delayed process from writing to your database. What matters here is that if a node's lock expires due to a network delay, but it still sends a write request to your storage layer, that storage layer will accept it unless you've built in extra protection. To ensure true correctness, you need validation at the storage layer itself. This usually involves something called monotonic ordering, where every lock comes with an increasing version number. The database checks if the incoming request's version is higher than the last one it saw. If it's not, the write is rejected. This failure mode, where a late write overwrites a newer correct write, is one of the most subtle and dangerous bugs in distributed computing. In an interview, always make it clear that the lock is the first line of defense, but the storage layer must be the final authority on whether a write is actually safe to commit. Fencing tokens are the secret weapon for making distributed locks safe. When a client acquires a lock, the lock manager also gives it a fencing token, which is just a number that increases every time a lock is granted. What matters here is that it provides a way for the storage layer to identify and ignore requests from zombie processes that have lost their locks. Imagine process A gets token 33, but then it hits a long GC pause. The lock expires and process B gets the same lock with token 34. Process B completes its work, then process A wakes up and tries to write using its old token 33. The database sees that it has already processed token 34 and simply rejects the outdated request from A. This failure mode prevention is essential for absolute data integrity. In an interview, if you mention fencing tokens, you're signaling that you understand the deep consistency issues discussed by experts like Martin Kleppmann. It's a high-level concept that proves a lock isn't a magical shield, but part of a larger, coordinated safety protocol between the lock manager and the database. Clock drift is one of those silent killers in distributed systems that can turn a perfectly designed locking strategy into a mess. We often rely on wall clock time to determine when a lease expires, but in a distributed environment, no two clocks are perfectly in sync. If one server's clock runs slightly faster than the others, it might decide a lock has expired and release it, while the actual lock holder is still busy processing. What matters here is that it breaks the fundamental guarantee of mutual exclusion. The failure mode here is catastrophic. You end up with two different processes believing they both have the exclusive right to write to a resource. This is exactly why we can't trust local system time for critical safety properties. In an interview, mentioning how NTP sync issues or hardware clock instability can compromise your lock's validity shows you're thinking about real-world physics, not just abstract code. It's a sophisticated point that demonstrates you understand why we need more robust mechanisms, like logical clocks or fencing tokens, to protect our data from the inaccuracies of physical hardware. In an interview, you're often asked if a distributed lock is even the right tool for the job. It's a bit of a trap because sometimes the best lock is no lock at all. You've got to weigh the complexity of managing a distributed lock against simpler alternatives, like using database-level transactions or optimistic concurrency control with version numbers. Distributed locking adds a lot of moving parts and latency, and it can become a massive bottleneck if every request has to wait on a central lock manager. The failure mode here is often a distributed deadlock or a performance collapse where the system spends more time managing locks than doing actual work. You'll want to show the interviewer that you're not just picking a shiny tool, but actually calculating the trade-offs. If your database supports ACID transactions, that's almost always a safer and faster bet. We only reach for distributed logs when we are coordinating across different types of resources, like a file system and a database, where no single transaction can cover the whole operation. Showing that restraint is key. We've just unpacked how distributed locking handles the chaos of multiple processes fighting for the same resource. To keep things consistent, we rely on mutual exclusion, ensuring only one owner holds the keys at a time. We explored two main lock types, exclusive locks for total isolation and shared locks for concurrent readers. In a system design interview, you've got to be ready to explain why we use lease-based locks with a TTL. It's our primary safety net against orphaned locks if a process crashes. Whether you're leaning on Redis with Redlock or a consensus-heavy tool like Zookeeper, the trade-off is always between performance and strict correctness. You've now got the mental model to coordinate shared resources effectively without risking race conditions. Well, that's the foundation of distributed locking mastered. That wraps up a look at distributed locking. When you are in an interview, remember that a lock isn't a magic fix. You've got to show you understand the failure modes. Be ready to explain how fencing tokens prevent delayed processes from corrupting data and why relying on local node clocks is usually a bad move. It's all about that trade-off between complex coordination and simpler database transactions. If you're finding these deep dives helpful, go ahead and subscribe to the channel. In the next episode, we will discuss sidecar pattern, where we'll discuss situation, core understanding, definition. Good luck with your preparation.